It rises in the east and bathes our planet in light. It powers the machinery of nature, our weather, encourages and sustains life on land and at sea, where it warms our oceans from pole to pole. When it sets in the west, it reveals to us its many billions of sibling stars, populating the night sky. We study our sun closely, and like a Rosetta Stone, it can reveal the secrets of all the other stars. You cannot study the sun in isolation. The influence of its power throughout the solar system it created is persuasive and dominating. The heliosphere is an immense magnetic bubble extending beyond the orbit of Pluto. It contains the solar wind of high and low-speed energetic particles and plasma that originate at the surface of the sun. After traveling for 36 years and 19 billion kilometers, the Voyager 1 spacecraft has reached the edge of this heliosphere.
Voyager 1 has left the bubble around the sun and entered interstellar space, the space between stars.
There, it still senses the shock waves emitted by the sun, which sound like this. To understand this source of power and its influences, scientists conduct observations from the ground and in space, where a flotilla of satellites train sophisticated sensors upon the sun and the space weather it creates.
Space weather is the field that studies how what's going on the sun affects us here on the Earth in our near space environment and on the space environment on other planets. The effects of space weather are so complicated because we have to understand what's going on at the sun, as well as all that stuff traveling through interplanetary space, how that affects us here on the Earth and throughout the heliosphere, that we need an entire fleet of instruments to look at these various effects. It's basically a system science, so you understand one part of it in order to understand the other part of it, and you have to put that whole puzzle together to understand the full effects of space weather.
GOES-P is an ongoing series of Earth observation satellites that happen to keep a constant eye on the sun, monitoring this space weather.
So when the spacecraft's sitting in space, it's looking down at the Earth and it stays stationary like this. But this solar array out here moves and tracks the sun. So that way, it's always looking at the sun and can take a scan every minute.
The sun's outer atmosphere is constantly being heated up by the solar surface. And this causes particles from the sun's atmosphere to stream away constantly. These streaming particles, which are filling our entire solar system, are called the solar wind.
Different phenomenon from the sun is constantly bombarding the Earth. Although you might not know it, the solar weather affects you every day down here as well. Not only just astronauts, it affects people on Earth.
The latest generation of GOES satellite is the GOES-R, soon to be launched into orbit. Other low Earth orbiting platforms include ESA's microsatellite Proba-2, testing new technology, and PICAR, sponsored by CNES, the French space agency. Hinode is the Japanese word for sunrise. It is a joint mission between JAXA, NASA and ESA to study the sun's magnetic cycles. Its close-up study has revealed the complex granular textures of the sun's surface and insights into solar flares.
A solar flare is a huge release of energy that converts the magnetic energy of the sun into heat, into light. It accelerates particles and can really heat up the plasma in order of minutes to over 60 million Kelvin.
For a large eruption, the sun produces a flash of light, which we call the solar flare. It also produces a huge ball of material traveling away from the sun we call coronal mass ejection. And both of those phenomena can accelerate subatomic particles, which we call solar energetic particles. These three things together make up a solar storm.
To study the solar wind phenomenon, a group of satellites were placed in a unique orbit between Earth and the Sun at what is called L1, or Lagrange point 1, a point of gravitational balance between the Earth and the Sun. The Advanced Composition Explorer, or ACE, observes energetic solar particles. WIND studies radio waves and plasma that occur in the solar wind and in the Earth's magnetosphere, and SOHO, the Solar and Heliospheric Observatory.
Using SOHO and using a technique called helioseismology, very similar to seismology on the Earth, we were actually able to see inside the sun. And so what we were able to do is see the layer of the sun just below the visible surface that we call the convection zone. And that's where all sorts of dynamics are going on. The inside of the sun is bubbling up to the surface. And that's really where all of the solar phenomena that we see is first developed. And so we were able to see underneath the surface and see these flows of solar plasma, see the formation of sunspots. And this is something that's never been done before. We're actually able to see the details inside of a star.
Another high-resolution space telescope was TRACE.
You're seeing details of the coronal loops. In the previous images you would from other satellites, it would look like it was just one big loop. And when you actually get to see TRACE, you can see it's all these teeny tiny, they almost look like threads. And there's these teeny tiny loops, and they're just breaking off and reforming and throwing plasma.
Using X-ray and gamma-ray solar flare imaging, RISI explores the particle physics behind solar flares. Another event subjecting the solar system to bombardment is the CME, or coronal mass ejection event.
A coronal mass ejection, or CME, is an eruption of plasma from the sun that shoots out into space, and it could affect us here at Earth if that big ball of plasma were to hit us.
NASA's twin stereo mission has one spacecraft orbit the sun ahead of the Earth and the other behind, providing a stereoscopic view of the sun to better understand these coronal mass ejections and the energetic particles of plasma.
Solar energetic particles are particles of plasma that are accelerated at the flare site from the energy that's released in the flare. And these particles could be accelerated up to almost 80% of the speed of light.
And a coronal mass ejection, when it's traveling so fast, creates a shock, and that can create solar energetic particles.
In 2009, NASA commenced a new scientific program called Living with a Star. The crown jewel of this program is the Solar Dynamics Observatory, or SDO, the most advanced spacecraft ever designed to study the sun and its dynamic behavior. The program's goal is to develop the scientific understanding necessary to address those aspects of the sun that directly affect us here on Earth. The spacecraft provides 16-megapixel ultra-high-definition imagery of the sun in 13 different wavelengths. From extreme ultraviolet frequencies to the helioseismic and magnetic imager and the atmospheric imaging assembly, each wavelength was selected to highlight a particular part of the sun's atmosphere. The results are stunning. They reveal fine details from the solar surface to the upper reaches of the sun's corona. These solar events dwarf our planet, and the science has brought a renewed focus back to Earth's protective magnetic field.
We are protected here on the surface of the Earth from solar flares and coronal mass ejections when they impact the Earth, due to the magnetic field of the Earth called the magnetosphere, which deflects the magnetic field and the energetic particles, as well as the atmosphere, which absorbs the higher levels of radiation.
Fortunately, we are protected here at Earth from flares and coronal mass ejections by the Earth's outer atmosphere. It absorbs a lot of the energy from the increased light from solar flares. But we're also protected by the magnetic field. You know, the Earth has a North Pole and a South Pole. Anyone who has a compass knows that. But this magnetic field of the Earth also protects us from these charged particles, the plasma coming from coronal mass ejections that largely deflects a lot of this direct energy. A coronal mass ejection will come and affect the Earth's magnetic field, and changing and hitting the Earth's magnetic field causes other changes on the actual far side, away from the Earth, that then accelerates more particles and shoots those particles then into the North and South Pole that produce these very beautiful waves of green and blue and red that are just lovely to see.
The sun is powered by a process called fusion, and that happens at the very core of the sun, where it is so intense, so hot, and so dense that protons fuse together and create helium. And this process fuels the sun and creates energy.
As the energy moves outward, boosted by magnetic fields, the temperature drops.
Up until that point, everything makes sense in that the hottest part is in the middle and everything gets gradually cooler as we move away. But then something very interesting starts to happen, which is that it starts to get hotter again.
This layer, where the temperature begins to rise again, is called the chromosphere. It lies between the photosphere and the corona, which is the hottest part of the sun's atmosphere. To discover how this corona is powered, another mission called IRIS was launched in 2013. IRIS carries a single ultraviolet telescope and imaging spectrograph, whose tight resolution allows it to see features as small as 240 kilometers on the sun's surface. IRIS's first images showed a multitude of thin fibril-like structures that have never been seen before, revealing enormous contrasts in density and temperature occurring throughout the region.
The light from the chromosphere is difficult to interpret because of the complicated interaction that the light has with the matter. It bounces around, if you will, many times before its final bounce towards us. And this means that that interaction between light and matter needs to be modeled in great detail, due to not just advances in computational power of computers, but in the computational techniques that have been developed by the IRIS team. We are in a position to do this.
Data collected from the IRIS spacecraft has shown that the interface region of the sun is significantly more complex than previously known.
Although the corona is extremely hot, millions of degrees, it's at a low density, so it doesn't actually take a lot of energy to heat it to that temperature. The chromosphere, on the other hand, is a much higher density, albeit lower temperature. And there's much more energy deposited in the chromosphere than the corona. So that a tiny fraction of that energy in the chromosphere escaping into the corona is plenty to power all of the processes that we see, from heating to such extreme temperatures to driving the solar wind that fills the whole solar system, impacting all the planets, including our own. We hope to better understand these fascinating and important processes with IRIS.
This energy streaming from the sun causes other knock-on effects on the planets of the solar system.
The northern lights are particles that are being shot into the North Pole and the South Pole that produce these beautiful greens and blues and reds. They're not direct particles from the sun. a coronal mass ejection will come and affect the Earth's magnetic field, and changing and hitting the Earth's magnetic field causes other changes on the actual far side, away from the Earth, that then accelerates more particles and shoots those particles then into the North and South Pole that produce these very beautiful waves of green and blue and red that are just lovely to see.
Armed with more questions about the solar wind and energetic particles, NASA launched a pair of probes into Earth orbit. Named after the famous scientist who discovered the radiation belt surrounding our planet, the Van Allen probes were dispatched to study the radiation phenomenon and the magnetic fields around the Earth in greater detail.
During the course of geomagnetic activity, disturbances caused by flares on the sun, by big blobs of plasma coming out from the sun towards the Earth, the Earth's magnetic field is battered and shaken. Some of that energy is captured in the Earth's magnetic field, and through a variety of processes, that energy energizes particles in the Earth's radiation belts up to energies that are hazardous to spacecraft and astronauts. The two spacecraft are focused on the dynamic radiation belts in the Earth's inner magnetosphere. They're the only spacecraft that focus on those. Consequently, they're a critical component in the series of phenomena that link the Sun to the Earth.
Solar flares and CMEs are all driven by magnetic reconnection. This is where the sun churns up the magnetic field that's inherent in it, and then it causes oppositely directed magnetic fields to then annihilate. But you can't just get rid of magnetic field. You can't just get rid of energy. You have to convert that energy and transfer that energy into other things, such as plasma motions, accelerating the plasma, heating up the plasma, and also giving out more light.
We are protected here on the surface of the Earth from solar flares and coronal mass ejections when they impact the Earth due to the magnetic field of the Earth called the magnetosphere, which deflects the magnetic field and the energetic particles, as well as the atmosphere, which absorbs the higher levels of radiation.
But this magnetic field of the Earth also protects us from these charged particles, the plasma coming from coronal mass ejections that largely deflects a lot of this direct energy.
The phenomenon of magnetic reconnection is not well understood, so NASA has launched a multi-satellite mission called MMS to try to unlock the secrets of our magnetic field.
The MMS mission is a mission consisting of 4 spacecraft which will fly in close constellation to measure a process called magnetic reconnection.
The universe is full of plasma and it's full of magnetic fields, and all over the place in the universe you have one plasma colliding with another. An example of that is the solar wind coming in and colliding with Earth's magnetosphere. And then the magnetic energy in the plasma, some fraction of that magnetic energy is converted very rapidly into plasma energy. So you can think of it as kind of like a magnetic explosion. And the reason this is important is because these explosions drive a lot of the weather patterns that we see in the magnetosphere, and so what space scientists like to refer to as space weather. And these space weather phenomena can have impact on our everyday lives. It can actually affect communication satellites, the power grid. So we'd really like to understand how these magnetic explosions work.
We need to measure reconnection in more than one location. We need to measure it in basically how it varies in space, how it varies in all 3 spatial dimensions. And that requires a tetrahedron. The additional fantastic benefit that provides is that it will actually enable us to recognize that we are looking with a reconnecting region much easier than a single spacecraft.
The ideal situation is that we would like the 4 spacecraft to kind of be surrounding this region where the explosion is happening. So the separation of the spacecraft is about 10 to 100 kilometers, which may seem like a long distance. But in terms of the magnetosphere, which is absolutely huge, this is really a microscopic region that we're trying to cover.
MMS has, in a nutshell, 2 orbital phases which are designed to study reconnection.
On the day side, basically you have a situation where the solar wind is just constantly running into Earth's magnetic field. And this is really great for MMS because we know that at some point MMS is going to encounter this region, and our hope is that since this process is always happening, we're going to get lucky and actually fly right through the magnetic explosion as it's happening. Now on the night side, the situation is a little bit different. So what happens is you have a more gradual buildup of magnetic energy in the tail, and these reconnection processes, these magnetic explosions, can just sort of pop off randomly. We don't really know when it's going to happen or where it's going to happen in the tail.
We need to understand both of those if we want to understand how the magnetosphere works, and we believe that both of those scenarios are also very important for other applications, such as on the sun, in the solar wind, in planetary magnetospheres, and in many astrophysical objects, as well as in the laboratory.
We hope that it's going to allow us to improve our models so that we can put the right physics in it and actually make predictions about where and when reconnection is going to happen, and this will help us make our space weather models more predictively powerful. The instruments that are actually going to be measuring the particles in space are collecting them much more rapidly at a much higher cadence than they have on previous missions, about a factor of 100. So whereas it would take a previous generation particle instrument about 3 or 4 seconds to build up the whole picture of the sky, it's going to take MMS about 30 milliseconds. So it really is sort of game-changing technology.
The current 24 or so operating satellites will be enhanced with new missions under development. The Japanese Space Agency will be launching their next solar physics satellite, Solar C. The Indian Space Agency will be launching Aditya to study the Sun's coronal mass ejections and magnetic field structures. The Deep Space Climate Observatory will maintain real-time solar wind monitoring capabilities critical to the accuracy and lead time of space weather alerts and forecasts. The European Space Agency's solar orbiter will be launched in 2018 and fly closer to the Sun than the planet Mercury to study how the Sun creates and controls its heliosphere. Also planned for a 2018 launch is NASA's Solar Probe Plus. It will approach the Sun more closely than any other probe before, at just 3.8 million miles from the surface of the star. Scientists have long wanted to send a probe through the Sun's outer atmosphere. The spacecraft will be exposed to temperatures approaching 1,370 degrees Celsius. Together, they will continue to monitor, study, and discover the secrets of this nuclear anvil that supplies us with light and life. Aside from the science, the images captured reveal to us the beauty and power of this, our nearest star, in all its grandeur.